Hi class, and we're on to lab 7 of CHEM111 labs. In this lab we're using a chemical reaction to inflate airbags. The purpose of this lab is to really understand how an airbag system works, but more so to use stoichiometry, percent yield, and our newest concept, which is called the ideal gas law, to find amounts that are needed to conduct this experiment. So let's go ahead and start our pre-lab lecture. Just a reminder, you should read chapters 11.2 and 11.3 in order to gain a better grasp of this experiment. In addition, of course, please read your introduction as well as the entire experiment before you listen to this pre-lab lecture video. Alright, so let's go ahead and state our goals. So after having read through our experiment, we can understand that we have several goals for this lab. The first goal is to design an airbag system based on a specific reaction, which is the gas-forming reaction of baking soda and vinegar. So that's the design component. The conceptual component is really to use stoichiometry, which you should all be familiar with by now, percent yield, which you should also be familiar with by now, and the newest concept, the ideal gas law, which I'll go over in this lecture video as well as in lecture next week. You're going to be using these three concepts to find amounts needed. Now, before we go into the heavy-duty calculations portion of this pre-lab lecture, let's just kind of review some properties of gases. So early in the semester, we said gases have no fixed volume or shape. And what we mean by that is that they can expand or compress to fill the containers they're in. And like I just said, they're also highly compressible. Gases are known to have extremely low densities. So think about it, right? If you have a solid piece of lead, that's very high density compared to, for example, oxygen or even air. The physical condition or the state of a gas is defined by really 4 different concepts, and we have a part 2 for this pre-lab lecture that emphasizes these concepts. But let's just kind of state these physical condition or a gas, what they're defined by. They're defined by temperature, they're defined by pressure, by volume, and by the amount of gas, and we refer to that as the moles. So how many moles of gas do we have in an equation? So again, we're going to go over this in greater detail in part 2 of our pre-lab lecture video for this week. So I stated an ideal gas equation. We'll go into the theory behind ideal gas equations in lecture, but to kind of state it for you here so you understand what we're working with, the ideal gas law states that pressure times volume is equal to the number of moles times the ideal gas law constant, so this is a constant, times temperature. So here our pressure is in units of atmospheres, and we abbreviate that as ATM. Our volume is in units of liters, which is lowercase l or uppercase L. Of course, it could be in milliliters, microliters, etc. By now, you are comfortable enough with unit analysis to convert from different units, from one unit to another unit. N stands for moles, and we're not using lowercase m for moles because that's typically understood as mass. So N is always understood as moles in chemistry. R, as I mentioned, that's our ideal gas constant. And it's a constant, which means it's a value of 0.08206 liters times atmospheres over moles times Kelvin. That dot right there means times. And lastly, your temperature, which has to be in units of kelvins, because notice that that's also units of Kelvin. Atmospheres is atmospheres, liters is liters. Remember from early in the semester, either our first or second lecture of the semester, we said if you have temperature in Kelvin, or excuse me, if you have temperature in degrees Celsius, you can find temperature in Kelvin by taking that temperature in degrees Celsius, adding 273.15. And that's how you get temperature in Kelvin. The ideal gas law, so this is the ideal gas equation. Now, the ideal gas law basically assumes that molecules of an ideal gas do not interact with one another. So they don't see one another at all. Again, I'll go over that in heavy detail in lecture. One thing I want you to pay attention to is this nomenclature called STP. STP stands for standard, temperature, and pressure, and the value of STP is 1 atmosphere for pressure, and standard temperature is 273 Kelvin, which is equivalent to about 0 degrees Celsius. All right, so that's it for concepts for now. Again, there's a part 2, so please make sure you listen to part 2 and do the worksheet for part 2. But I actually want to go over what you're actually doing in lab this week. So this experiment has 2 parts. The first part is volume measurement of a gas to determine % yield and reaction time. So as I mentioned, we have an airbag model system in this lab. So our model system is sodium bicarbonate reacting with acetic acid, so this is actually baking soda reacting with vinegar, to yield carbon dioxide, sodium acetate, and water. So if you notice part A, step 1 of part A, and again, please pay attention and bring this to to lab, says that you need to determine the number of grams of baking soda needed of sodium bicarbonate to generate about 80 mils of CO2 gas, assuming you have 100% yield. So let's first, remember, whenever you see a chemical equation, make sure you balance it first. Let's see, okay, this is actually balanced, so we're good. So what do we want to find from step 1 of part A? Well, here we're saying we need grams of sodium bicarbonate, and we want enough grams to yield 80 milliliters of carbon dioxide gas. And here I'm telling you your yield is 100%. So all of my reactants are converting 100%. I'm assuming that they're converting 100% to my products. So how do I determine the number of grams of sodium carbonate needed to generate this amount of CO2 gas? Okay, let's kind of on the side here think about these steps. Well, I'm given 80 milliliters of CO2 gas. So I know I can only, whenever I'm given a chemical equation, what we went over in the last chapter, in chapter 9, is, well, your coefficients are giving you that constant relationship between one substance to another substance, etc. So here we have 1 mole sodium bicarbonate, 1 mole of acetic acid, 1 mole of carbon dioxide, 1 mole of sodium acetate, and 1 mole of water. Here I'm given, and remember, we can only go from moles to moles in a chemical equation. If we're given something else, that means we have to convert that to moles. So our first step is actually to find moles of CO2, and since it's a gas, we're going to be using the ideal gas law. So that is the newest component of this experiment. So then once we find moles of CO2, guess what? You're using stoichiometry to convert to moles of sodium bicarbonate, and then from moles of sodium bicarbonate, you're converting to using molar mass to convert to grams. You are all experts at this, at stoichiometry at this point. So step 2 is to use stoichiometry to find moles of sodium bicarbonate. And then as we just talked through it, step 3 is to use my molar mass of sodium bicarbonate to convert moles to grams. So that's kind of my roadmap to kind of allow me to really understand what I'm doing. I'm given 80 milliliters of CO2. I just introduced to you ideal gas law, or the ideal gas equation, which actually relates volume of a gas to moles of a gas. That's great. And then from there on, we use stoichiometry and molar mass. So let's go ahead and do this. So we're going to make the assumption that CO2 is an ideal gas, and we're going to assume that we're at standard temperature and pressure, okay? Just make that assumption for this lab. I'll explain it more in lecture next week. So that means we can use PV and RT. If we're interested in this step again to finding the moles, so rearrange this equations to solve for moles. So when we do that, we get PV over RT. Now let's plug in everything that we have. So standard temperature and pressure is 1 atmospheres times our volume has to be in liters because our ideal gas law constant is also in liters. So convert this to liters, 0.0800 liters over my ideal gas constant is 0.08206 liters times atmospheres per moles times Kelvin, and STP means my temperature is 273.15 Kelvin. These kelvins cancel out, these liters cancel out, these atmospheres cancel out, and now I have 1 over inverse of moles, which means my moles are on top. So now if I plug this into my calculator, my moles of CO2 is 0.00357 moles of CO2. So now step 2 says, well, once I find moles of anything in my chemical reaction, I can actually use stoichiometry to convert it to moles of something else. So let's go ahead and do that step. I have moles of CO2. I'm desiring moles of sodium bicarbonate, and here we have a 1-to-1 ratio, so 1 mole of sodium bicarbonate over 1 mole of CO2. Mole of CO2 cancel out, and we get 0.0035 moles, 357 moles of sodium bicarbonate. Now step 3, as we've done several times in chapter 9, we use our moles of sodium bicarbonate, we multiply it directly by the molar mass of sodium bicarbonate, so you should calculate this on your own. And as always, if this is going too fast for you, the great thing is about recording, pause, rewind, re-listen. Okay, so these cancel out. So I calculate it to find that I need 0.300 grams of sodium bicarbonate in order to generate 80 milliliters of CO2. All right, great. So that's sodium bicarbonate. Now I need to do the same for acetic acid. So in your procedure, you'll notice that part 2, so we just did part 1 together. Now let's do part 2. Determine the number of milliliters of acetic acid needed to generate 80 milliliters of CO2 gas. Again, we're assuming 100% yield. So let's go through this calculation. So one thing I want you to notice, this capital M, you've seen it probably countless times in lab now. This capital M stands for molarity, which we'll visit when we start talking about solutions in a few chapters. And molarity, it's basically moles over liters. All right, so let's go through this. So step 1, we're not doing anything different here because we already have our moles of CO2. So moles of CO2, we already calculated that above using the ideal gas law. Okay, now step 2 here, so here we want to find milliliters of acetic acid. If we know our molarities as moles over liters, if we find moles of acetic acid, then we can find liters of acetic acid and then milliliters of acetic acid. So I need to figure out how many moles of acetic acid do I have using stoichiometry. So here we have 0.00357 moles of CO2. Our stoichiometric ratios are 1-to-1. So it's times 1 mole of acetic acid, CH3COOH, per 1 mole of CO2. My moles of CO2 cancel with my moles of CO2. And I know you can tell that it's going to be the same number. I'm going through these steps so that we are reviving these concepts in our mind. So through this calculation, through stoichiometry, I figured out that I need 0.00357 moles of acetic acid. Think of molarity this week as a conversion factor, okay? My third step, now use molarity to find liters and then to find milliliters. Okay, so let's go through this carefully. I just told you that molarity, which is capital M, is equal to moles over liters, okay? So why don't we rearrange this to solve for liters? So therefore, liters is equal to moles over molarity, okay? So now let's actually plug in what we have. We just figured out our moles, 0.003, and we're doing this for acetic acid, 357 moles over my molarity of acetic acid is 1.0 moles per liter. Moles cancels by moles, and now I have 1 over something, so therefore my liters comes on top. So I get 0.00357 liters. Now I need to convert liters to milliliters, so this is going back to chapter 2, beginning of the semester. 0.00357 liters times, I know there's 1,000 milliliters in 1 liter, and I find out that I need 3.57 milliliters of acetic acid. To produce 80 milliliters of CO2 gas. Again, if this went by too fast for you, pause, rewind, go over this again. We're using new concept of ideal gas law to convert 80 milliliters of CO2 to moles of CO2. Then we're going back and using stoichiometry to go from moles of one substance to moles of other substances. And now we're using a new concept called molarity, which again, just think of this as a conversion factor for now. And that's allowing us to find our liters of solution and then finally milliliters of solution, because that's what you're actually measuring in lab. So then at this point, we found number 2, and now go ahead and do steps 3 through 8. There's a lot of interesting manipulation happening here. So instead of glass beakers, we're going to actually give you guys plastic tubs to give you and your lab mate more room to be able to invert this. Be very careful to not allow the graduated cylinder either to tip over, and also this tubing has to be immersed into the graduated cylinder. Your lab instructors can demonstrate this. If you have questions, again, just email any one of us and we should be able to answer your questions for you. All right, great. Now let's go on to part B. So part B is called inflating an airbag. So here, in part B, we want you to determine the volume of the small plastic bag. So we're going to give you guys a small Ziploc bag, and you're actually going to make an airbag in lab out of this Ziploc bag. You need to determine the volume of this plastic bag. I want you to describe how you actually did this, okay? You're actually graded on how you do this. Be creative. I'll leave it at there. Be creative how you're going to figure out the volume of this plastic bag. When you figure out the volume of the plastic bag, calculate the quantities of sodium bicarbonate that you need and acetic acid that you need to inflate the small bag with the highest percent yield possible in the shortest amount of time from part A. So I know we skipped ahead from these parts, but if you read carefully, this will make a lot of sense to you. So there's still some calculations necessary for part B. Make sure your volume for the plastic bag is milliliters. Is in milliliters, okay? Okay, a couple of logistics here. You're going to be working in pairs. This experiment is impossible to do it on your own, so make sure you work in pairs. This lab, as I said, takes a fair amount of coordination to invert your graduated cylinder, insert the tubing into your graduated cylinder, and then what you're going to be doing at that point is you're knocking over a plastic vial. Read the procedure, it'll make sense. Make sure you're conscious of how you put the tubing up and into the graduated cylinder. If it's too close to the outlet of the graduated cylinder, the tubing is going to actually come out and you're going to have to restart this. So actually from previous years, the thing that really takes the longest here is students, the tubing actually escaping the graduated cylinder, and you'll have to restart it, okay? You have obviously you have your traditional lab notebook. Oh. This week you have a lab quiz, which is open notes, so that means you can use this pre-lab lecture worksheet. Not your lab notebook though, just the pre-lab lecture worksheet. And you also have a post-lab assignment, which is due in lab the following week. Don't forget to pass in post-lab assignment number 6 at the start of lab, okay? No late assignments will be accepted. Okay, that's it for this portion of the pre-lab lecture video. There will be part 2, so make sure you go ahead and listen to part 2.